Before we get into shorthand notation, let's review the structure of a galvanic or voltaic cell. Remember, a voltaic cell uses a spontaneous redox reaction to create an electric current. And so we already know what happens on this electrode on the left. The zinc electrode, the solid zinc, turns into zinc 2 plus ions. So think about an atom of zinc turning into zinc 2 plus. The atom would have to lose 2 electrons, so 2 electrons are left behind on the zinc electrode. Let's write out that half reaction. So we have solid zinc, right, losing 2 electrons to turn into zinc 2 plus ions in solution. So this would be losing 2 electrons, so we put the electrons on the product side. And this is our oxidation half reaction. So this is an oxidation. So we lost electrons. And remember, when you lose electrons, it's an oxidation reaction. Or you could also look at the oxidation states. Those 2 electrons that we lost, these 2 electrons right here, are going to travel along our wire. So we have a wire set up, and those 2 electrons are going to move, which is our electric current. Right? So we get an electric current in our wire, and those 2 electrons move over to the electrode on the right, which is copper. So now we have these 2 electrons on our copper electrode. In solution, this is an aqueous solution of copper sulfate, so we have copper 2 plus ions in solution. And when those copper 2 plus ions come in contact with those electrons, right, we get a reduction half reaction. So let's write it out here. So copper 2 plus ions, right, are going to gain 2 electrons. Gain of electrons is reduction. So think about what happens if you add 2 electrons to a copper 2 plus ion. You get solid copper, right? So overall 0 charge. So this would be solid copper. And since we gained electrons, this is our reduction half reaction. So this represents a reduction half reaction. So remember, loss of electrons is oxidation, and gain of electrons is reduction. So Leo the lion goes grr is a good way to remember oxidation and reduction. If we add together our 2 half reactions, we get our overall redox reaction. So we add these together, and we know that the 2 electrons that were lost by zinc are the same electrons that are gained by copper 2 plus. So we can cancel those out. And so for our reactants, we would have solid zinc, and we would have copper 2 plus ions. So we write that in here. So solid zinc plus copper 2 plus ions. And for the products, right, over here we would have zinc 2 plus ions and solid copper. So this gives us zinc 2 plus ions in solution and also solid copper. So over time, if you think about what happens, right, we're losing zinc. So let me use a different color here. So we're going to lose zinc over time, and we're going to gain copper. Right? So we're going to get more copper deposited on our copper electrode. So think about more copper deposited on the surface of our copper electrode. So that's our spontaneous redox reaction that's creating an electric current because of the flow of the electrons in the wire here. Let's go back to our half reactions and think about the electrodes. So we know that oxidation occurs at the anode, right? So this must be our anode, and we know that reduction occurs at the cathode. So this must be the cathode. And a good way to remember this is anox and red cat, right? So anox, oxidation occurs at the anode, and then red cat, let me write that one down over here. So red cat, reduction occurs at the cathode. All right, let's also think about the salt bridge really quickly. Right, so we have, let me go ahead and use red here. We have sulfate anions in our salt bridge, and anions migrate to the anode. So anions migrate to the anode, so that's easy to remember that. So these anions are going to migrate this way, and cations migrate to the cathode. So we have sodium cations here, and cations migrate to the cathode. So it's easy to remember what's happening in the salt bridge. All right, now finally let's think about shorthand notation. So it's a little bit annoying to draw out a picture like this every time you want to represent a voltaic cell. And so there's a shorthand notation that's used, so you don't have to keep drawing things out. And so let's go ahead and start writing our shorthand notation. First, you put your electrode, you put your anode. So our anode here, our anode is zinc. So we have solid zinc. So let me write that down here. So solid zinc. Next, you draw a single vertical line, which represents a phase boundary between solid zinc and your aqueous solution of zinc 2+ ions. So we're going to write our zinc 2+ ions in here. So we've represented, let me use red for this, we've represented our zinc electrode, and we've represented our zinc 2+ ions. Next, we draw a double vertical line, and this represents our salt bridge. So the double vertical line represents our salt bridge. And next, we put copper 2+. So we have copper 2+, let me circle these in green, copper 2+ ions. So we write Cu2+. And next we draw a single vertical line again, representing a phase boundary, because now we put our other electrode, our cathode, and our other electrode would of course be solid copper. So let's go ahead and write that in. So we have solid copper right here. So the anode is always on the far left, and the cathode is always on the far right. And so it's easy to remember that because A comes before C in the alphabet. So the anode comes on the left side, and the cathode comes on the right side. And again, this is just the shorthand way of representing a cell. So instead of drawing out this huge picture, if you see this written, if you see all of this written, let me go and underline it here, all of this written in a chemistry textbook, it's just telling you the same information that's in this picture.